Welcome back to another episode of gas laws. Okay, now today the second aspect of the series of the episode of the gas law is going to be called Charles law. Charles law. By definition. So that's the number one objectives. We're looking at the definition of Charles law. Okay. We'll be looking at the mathematical expression of gas law. We'll also be discussing the graphical representation of gas law, and we'll be able to solve problems. These are what students or anybody that watch this video are expected to achieve at the end of this video. Okay, hope you are following. Now, let's take a look at what Charles law is. By definition, Charles law states that the volume of a given mass of gas, are you following that one? Is directly proportional to the absolute temperature provided that pressure is constant. You get it? The volume of a given mass of gas is directly proportional to the absolute temperature provided that what pressure is constant. Now, mathematically, let's look at it mathematically, we discover that V, okay, is directly proportional to what? To T, while P is what? Constant. Alright, introducing proportionality constant K, you're going to have V equals to KT. When you make K sort of formula, you have V over T. Now, when you vary this value, these two values, you're going to have what is called V1 over T1 equals to V2 over T2, which becomes what? It becomes our Charles law formula. It becomes our Charles law formula. We have the V1 here is the initial volume. V2 is the final volume, and T1 is the initial temperature in Kelvin, and T2 is what is final temperature in Kelvin. Now take note of this. Take note of this. I'm trying to draw something. Please take note. Now this one is telling us I have V1 here, for instance. I have V2. I have V3. I have V4, and I have T1, I have T2, I have T3, I have T4. What does this one shows us? It shows us that the higher the volume, the higher the temperature. Did you get that? The higher the volume, the higher the temperature. Now, let's look at the graphical representation of Charles law. The graphical representation of what? Of Charles law. Okay. Graphically, gas law can be represented in the following. Number one, you can have this. Okay. This is going to be extrapolated. Okay. This is going to be volume, cube. It's going to be temperature. It's going to be what? In degrees Celsius. And it's going to be minus 273. This. Okay, it's going to be my volume as against my what? my temperature in Kelvin pass through the origin. Okay, while the last representation of Charles' law will be in this manner: V over T going straight to V over T, V over T. Alright, those are the graphical representation of Charles' law. Hope you get it. Good. So let's proceed quickly. Let's proceed. Now, Charles' law has its standard units. Okay, what are the units in Charles' law? We have volume. Volume is either a dmq or cmq. Okay, while temperature is Kelvin. Okay, temperature is what? Kelvin. All right. Now at STP okay, at STP my temperature is 273 degree Kelvin. So all the temperature given under Charles' law in Celsius must be converted to what? To Kelvin. And how do you do that? You can use this formula by saying Kelvin equals to Celsius degree plus 273. In other words, when you are given a particular temperature under our Charles' law to calculate, you are going to be converting that temperature from Celsius degree to what? To Kelvin. Okay, let's take an example of some of those questions that will help us. Okay, let's quickly look at example 1. Example 1. A fixed mass of gas has a volume of 92. At 3 degrees C. Alright, what will be its volume at 18 degrees C? If the pressure remain constant, what will be its volume at 18 degrees C if the pressure? So let's look at the board quickly. Let's look at the board together. Look at it. Our initial volume is V1. Our initial temperature is 3 degrees C, and our final temperature is 18 degrees C. And we have to state that if 30 cm3 of a gas at 50 degrees C is warm to 80 degrees C at a fixed pressure, the fractional increase in volume is what? You are directly calculating what? The volume. What's the fractional increase in the volume? Quickly, let's look at what we have. We are still looking at V2. Using our formula, V1 T1 equals to V2 T2. So, we're going to have something. Now, let's substitute our value. Now we have 30 over... Oh, we need to convert. Before we substitute, let's make our conversion. Remember, plus 273 plus 273. Okay, when you do that, what we have, quickly, student, let's do that. 273 plus 50. What do we have? Of course, we have what? 323 Kelvin. And 273 plus 80 we have what? 353 Kelvin. These are the conversion rates. Now let's place substitute. We are doing that. V1 we have what? 30 over 2, 323 equals to V2 over 353. Alright, our V2 will be what? 30 times 353 divided by what? 323. Our V2 will be our B2 will be 32.78, okay, cm3. Okay, that's what we arrive at. But we are asked to find the fractional, okay, the fractional increase in the volume. The fractional increase. So let's look at how to undo that particular question. Fractional increase in the volume. You know, we have our final volume to be this and our initial volume. Let's quickly look at what is the fractional increase. So we have 32.78 minus 30. We're going to have something of 2. Yeah, alright, look at it. Let's look at it. The volume, the increase in volume is going to be 2.8 cm3. But because it's fraction we are talking about here, so we are going to have 2.8 over the original volume. 2.8 divided by the original volume. I'll give us what? 0.0933 cm3. Alright. What is the value of -14 degrees C? Okay, on the Kelvin temperature scale, we are going to be using this formula K equals to degrees C plus 273. So we have our Kelvin in what? -14 degrees C plus 273 degrees C. To that you have something like 259 Kelvin. Okay, so if you have not subscribed now, please do like to subscribe to our YouTube channel. Alright, example 4. If 60 cm3 of a gas is heated from 27 degrees C to 50 degrees C, what is the new volume of the gas at constant pressure? Okay, so we are looking for V2. So let's use our same formula. V1 over T1 equals to V2 over T2. But of course, we are going to convert this value. We're going to convert the value. We have 273 plus what? 273. So when we add this one, we're going to get 300 Kelvin, 323 Kelvin. But let's obtain the value. V1 will be what? 60 over 300 equals to V2 over 323. So when you cross multiply, you have your V2 to be 60 multiplied by 323 divided by 300. So quickly, when you do that, we're going to our V2 to be 64. Example 5. Okay, let's look at example 5. Example number 5. Let's check the screen. Let's check the screen. It's a UTME question of 2020. It says, given that a mass of a gas occupy 1 dm3, a gas occupy 1 dm3 at temperature of 300 K. At what temperature will its volume be doubled, keeping the pressure constant? Okay, 2 dm3. Look at the screen. Okay, you can see there T2. Within temperature, initial temperature is 1 dm3. Final temperature is 2 dm3 because it's double of 1 dm3. So let's look at our same formula. We have V1 over T1 equals to V2 over T2. We're going to have 1 over 300 equals to 2 over T2. We are going to have, when you cross multiply, you have your T2 equals to 300 times 2 over 1. Your T2 equals to 600 Kelvin. Make it like classwork. Let's make it like classwork. Okay, now a gas initially at 273 Kelvin, alright, is heated such that its volume becomes twice. Its volume becomes twice of its original value. What is the new temperature? Very cheap question. What is the new temperature? We are looking for T2. Alright? They said the gas, the volume becomes twice. That means if I assume 1, 2 will be 2. If I assume the initial volume is 2, the final volume will be 4. Whatever you are assumed to be initial volume, the final volume will be twice of the value. So we can use our V1 over T1 equals to V2 over T2. So when you substitute that value, you have our V1 to be what? 1 over T1, which is 273, equals to V2, which is 2, and your T2 is what you are looking for. When you cross multiply, your T2 becomes 273 times 2 divided by 1. So your final answer now, T2 become 546 Kelvin. Alright, thank you for watching this video. Alright, make sure you subscribe to my YouTube channel. I'm signing out this night. Okay.